All right, this is going to be a little exploration of gamut and volume. To talk about this stuff, we're going to use these three images. We have a ramp, which goes from 0 to some maximum value, which we specify. In this case, it's 4. We have a primitive hue sweep, which is a linear interpolation of each of the color channels from minimum to maximum, or from 0 to 1. So we have red, which goes from 0 to 1, and then back to 0, whereas green goes from 1 to 0, and then from 0 to 1, and blue, etc. So we have a hue sweep from red to green to red to blue to green again. And then finally we have a CMS test pattern, which is a bunch of sample points. So to visualize these things, we're going to use two things. We're going to use this plot slice gizmo, which basically draws the values of the first scanline of pixels as a graph in X and Y. So if we look at this right now, it's displaying this ramp, and if we adjust exposure up or down, it's moving like this. And if we disable the clamp, we can see the values go above 1. So this range here is from 0 to 1 and then up to 2. And we'll also use this plot chromaticity points gizmo, which basically plots the RGB values directly in a 3D coordinate system. I have it set up so that the transform is set to none, which basically just takes the input RGB values and plots them in the 3D space. Cool. So, as every compositor knows, in scene referred we have no upper bound to the maximum brightness value that can exist. So values can go very, very far, way up there into the very bright regions, and way, way down here into the very dark regions. In a display referred medium, that is not possible. We have a finite range to represent brightness. It's encoded in display referred in a integer data coding, which means there is a range from 0 to 1, which can be represented as code values, which in an 8-bit integer code value would be 0 to 255, or 10-bit 0 to 1023. And basically, when we do that, we're clamping our input values into a 0 to 1 range. So if we look at what's happening with our plot slice, we can see that if we adjust exposure up or down, we're basically only keeping this range here from 0 to 1. Makes sense, it's pretty simple. So in a display transform, what we're trying to do is take that input scene linear brightness range and remap it into this narrow range of light that the display can emit from its minimum brightness value to its maximum brightness value. So I have here a slightly modified version of the original naive display transform gizmo, which has a linear section and a highlight compression. So if we turn this on, if we set this up, we can see what's happening. Right now, the linear black is mapped to 0, and the linear white is mapped to 1, and the display white is 0.5. So in this current configuration, the only thing that's happening is a value of 1.0 in scene referred is mapped to a display value of 0.5. And note, I have the inverse EOTF and the display colorimetry conversion turned off, so the only thing that's happening right now is this mapping. If we check that, we can see that indeed a value of 1.0 is changed from a value of 0.5, or to put it another way, if we change this, we're basically changing where the display white is mapped to. If we introduce highlight compression, we can compress from where the display white is specified. That's sort of our threshold for where the compression starts. So if we turn this on, we can see what happens. And right now, the maximum, which is the maximum value in scene linear to compress to display white, is set to 4. So we're taking our input scene referred value of 4.0 and we're compressing it down to a value of 1 between display linear 0.5 and 1.0. if we change where this maximum is, we can sort of set what scene linear value is mapped to 1. And if we change the strength, we can see it's adjusting sort of the slope of the compression curve. And if we change where d white is set, that's changing where the threshold of compression starts. So with this set to around 0.7, we have a larger linear range where we identically map scene referred linear input to display referred linear output. However, this leaves us with much less range for highlight compression, which doesn't look so great. So we set this back to 0.5. So that's brightness, and brightness is sort of the first step in this complex series of problems. So how does color come into the picture? And I guess when I say brightness, I should be using the proper term, which I guess would be luminance as brightness. Brightness is inherently a perceptual term, but color pragmatist, not color scientist, so I'm going to be butchering proper terminology left and right. All right, so brightness is a one-dimensional problem, right? Because we're taking the luminance, the input luminance, and changing that luminance value in output. So we're mapping input values to output values, which can be represented as a one-dimensional lookup table. Color is inherently three-dimensional because we have R, G, and B. So here you can see our basically scanline plot. Let me switch my viewer here. A scanline plot of those linear ramp values, so you can see visually what's happening. Here we have red coming up and green coming down. That forms green to red, etc. But if we switch this to 3 dimensions, we can see what this looks like. So here we have a triangle, which is formed in 3-dimensional space. This is not a chromaticity space. It's just mapping RGB values into 3 dimensions, which I think is maybe a useful way to visualize what's going on. So if we change our hue sweep settings, we can have the pivot here set to 1, and if we adjust the exposure up or down, that's basically, in this case, darkening. You'll have to forgive me, the position to points node in Nuke is pretty buggy, so it might flicker on and off, but it does do the job. So we have a ramp here that goes from 0 up to a value of 1 at the maximum. So red is around 1, and it goes down to 0, or a very small number, in this case 6 stops below 1. And yeah, so if we look at this, basically we have a sort of a pyramid shape, right? The red, green, and blue form sort of the axes, and the origin is at 0. And if we multiply the exposure of this up, if we disable our clamp momentarily, we can see that the R, G, and B values just go out in all of these 3 directions sort of infinitely, right? We're just making our pyramid bigger. But if we turn on our clamp to simulate what happens in a display referred medium, we can see that this is where the maximum of our red, green, and blue, and also cyan, magenta, and yellow form. And if I take our viewer here, which is set to none, and gain down, you can see that these values are in fact clamped to a maximum value of 1. And I'll just move this over here, and I'll actually change to looking through the inverse EOTF so that we can sort of visualize what's coming out of the display correctly. Okay, so if we expose this up and down, we can see that the position to point gizmo does not work reliably. Let's fit this again. Okay, apologies. It looks like if I have this viewer connected here, this does not update correctly, so I'm going to kill that and actually just set this viewer to be in sRGB so that we're seeing the right thing. Okay, So if we put this over here and we adjust the exposure of this hue sweep up and down, basically what we're seeing is Nuke crashing and burning horribly. Okay, we've restarted and it seems to be working again. So if we have this hue sweep, which goes from 0 to 1 luminance, and we expose up, we can see what happens when the display maximum kicks in. Basically, these hues start to clamp to the secondary and primary colors. So primary clips, and then the hues go towards the secondary, and they clip. So what can we do? Well, we could take the brightness, luminance of these values and compress them down. If we turn this on, we can see what happens. And basically, this will help. There's a more natural looking roll off between the brightness values, between the transitions of the tonalities as they go up towards the display maximum. But as we expose upward, we still run into the same problem. If we do another ramp here, this is set up to be a highlight compression from 0.5 mapping a maximum in scene linear of 4 to a value of 1. And if we graph that and look at what happens as we expose up, we can see that we don't get the... All right, well, it appears as though having two viewers updating at the same time is not working and it's crashing a lot. So we'll pause this viewer and we will do the same thing. So with our display transform on, if we expose our hue sweep up, we can see that as the values increase, there is a slightly nonlinear curve happening now as our primaries approach display maximum because of our highlight compression, our luminance compression. But the same thing still happens as we expose up. All of the values eventually clip to the display maximum, which if we unpause real quick, looks like this. And if we keep going to a ridiculous degree, eventually all of the values go to the purely saturated primary and secondary colors. So how do we solve this and make this look a bit more natural? In film, as exposure increases, the saturation changes and the value gets closer and closer to no emulsion left on the film. So the color becomes the color of the light shining through the film. To simulate something like this, we will need to engineer it if we are designing a chromaticity preserving display transform from scratch. So how do we do that? Well, basically, what we want to do is push these extremely saturated colors towards the sort of achromatic axis. If we put a saturation node here and desaturate them with maximum as our method, basically this is the corner of our sort of gamut cube, the volume of all possible colors that our display can output. And these are the fully saturated colors. So what we want to do is push these values towards this value. And there's this CMS test pattern here as well. If we plot what this looks like by default with no adjustments made to it, this is the cube of all possible colors representable at the display, from 0 in this corner to 1 in this corner, where all red, green, and blue channels are 1. And then in the other corners, we have our secondary colors, magenta, cyan, and yellow. And then again, as we saw before, on the axes, we have red, green, and blue. So if we were to desaturate this towards our achromatic axis using maximum, we can see all of these samples sort of converging towards the white corner. So basically what we want to do is take our more saturated colors and push them towards that corner as brightness increases, as luminance increases. Oh yeah, and if we expose up, we can see that the same behavior is happening where all of the, I'll just unpause this so we can see what this image looks like. all of the values sort of converge towards the fully saturated primaries. So all the corners are represented in those points. If we turn the point size up to 2, you can see. Cool. So if we turn on our display, our naive display transform again, if compress highlights is on and our maximum input value is still 1, it's going to be mapped to a dim value of 0.5. So let's boost the brightness of our input here a bit. So now we're getting values up to the display maximum in this corner and the other primaries corners. And if we continue to boost it, we'll see the same behavior where colors sort of clip to the fully saturated value. But if we turn on our desaturate highlights, which I guess could more properly be termed the path to white, and we turn this on, we can see what's happening. So as we increase exposure, now the path, the values don't sort of go up against the fully saturated axis anymore. They sort of form this sort of change direction slowly towards the white point as the brightness increases. So that's interesting. And if we look at the hue sweep and do the same thing, now we're looking at points only along the fully saturated edge of the gamut boundary, if you will. And we can sort of visualize what happens. So you can see that the gamut hole, or the outer boundary, is now no longer a cube. And if we turn this off, we can see that it is still a cube. So we're straight out to the corner of the maximum color representable. And if we turn this back on, we can see that the hue, the saturation of the colors is being sort of slowly non-linearly pushed towards the display maximum. Cool. So this shape is obviously missing some of these colors, but this rendering looks a lot more believable and photographic than the alternative. So we can also bias this curve. In the default state, as it's set up right now, the values are compressed towards the achromatic maximum point as the curve compresses more. So put another way, if we were to look at this through our slice and look at this. So as the values increase, there's no push towards the achromatic axis up until the sort of threshold of the shoulder compression, which is at 0.5. And then as this curve continues to compress values more and more, the values are pushed towards the achromatic axis more and more. Not saying that's a correct approach, but that's how this is set up. Right, so looking at this again, so we can change the bias of that curve. We are still getting some sort of unnatural corners here as the hues sort of approach the display maximum. If we push the black point up, we can sort of bias where the curve starts. So if you look here at the curve as it's coming down, if we boost the black point up, it's sort of defining where that curving starts from. And if we bring the white point up down, that's actually changing where it ends. So we can see if we lower this a little bit, we can actually get rid of those harsh corners here and form more of a smooth shape as it approaches the display maximum. And if we adjust the gamma, we can change sort of how the curve approaches, well, how it travels from the minimum to the maximum value using a power function. So using these three controls, we can sort of bias how that curve happens. Of course, we could approach this a different way, but this is just how it's implemented here as an experiment. So without desaturate highlights, and I'll show the image, and with desaturate highlights. And let's see if I can adjust the exposure. Yeah, not really. So path to white above display maximum. Hopefully this makes it a bit more clear what's actually going on.